Hello, welcome to this lesson of the Linear Algebra Tutor. In the last section, we got into the nitty-gritty details of what it means to have a solution of equations like this when we have an infinite set of solutions. We called it a dependent set of equations, or a solution that was dependent on the value of k that we select, or the value in that case of z that we select there. So we're going to work another problem, and that will be as follows. X plus 2y minus 6 times z is equal to 11. X plus 4y plus 4z is equal to 5. And then 3x plus 10y plus 2z is equal to 21. All right. Now, I'll tell you ahead of time, this is also going to be dependent as well. You cannot tell by looking at the system of equations outright that it's going to behave that way. So let's write our matrix. 1, 2, negative 6, 11, 1, 4, 4, 5, 3, 10, 2, 21. Now in the last problem, what I did is I just drew an arrow and I said, hey, there's some row reduction here. You're going to end up with this matrix. I wanted to skip those steps there because mostly what I wanted to focus on was the end game. What you get once you arrive at that, how do you arrive at the dependent form of the solution? An infinite set of solutions for a set of equations like this. Here I'm going to go and work all the steps of the row reduction to show you how you basically cannot get a diagonal matrix all the time and how it leads to this infinite set of solutions. So we have a 1 already here, so the next step in row reduction is we want to put a 0 underneath my leading column, which is already in this case a 1. So I'm going to leave the first row alone, 1, 2, negative 6, 11. And then I want to get a 0 here. So I'm going to say negative row 1 plus row 2. I'm multiplying this row times negative 1 and adding it. So I'm going to get a 0 here. Negative 2 plus this will give me 2. Negative times this will give me 6. So then 6 plus 4 is 10. And then negative 11 plus this guy is going to give me negative 6. So that gives me that. And at the same time, I can make this a 0 by multiplying this row by negative 3. So negative 3 times row 1 plus row 3. I'm not attempting to make this 0. So when I multiply this by negative 3 and add it, I get a 0. Negative 3 times this will give me negative 6 plus 10 is positive 4. Negative 3 times this is going to be positive 18 plus 2 is 20. And then negative 3 times this is going to give me negative 33 plus 21, which will give me negative 12. All right, so far I have done exactly what I have set out to achieve. I've got zeros underneath here. The next thing I want to do is put a 1 in the center of the matrix, and then after that I'll put a 0 underneath it. All right, now that I have my zeros here, the next thing I want to do is work on making a 1 in this position. And then after that I'll work on making a 0 underneath that. But the top row is not going to change during this process. So 1, 2, negative 6, and that'll be 11, like this. Now to make this a 1 here, I'll just multiply by 1/2 times row 2, which will give me 0, 1, 5, and negative 3. I just multiply by 1/2 across. And let's just, for the time being, keep the bottom row exactly as it is. Negative 112 there. All right, so the next thing I typically do after I make the center guy a 1 is I try to make a 0 underneath. So here I'll open this guy. Again, the top row is going to stay the same. 1, 2, negative 6, 11, like this. The middle row is going to stay the same. 0, 1, 5, negative 3. But the bottom row, I want to make a 0 here, so I'm going to multiply by 4. Negative 4 times row 2 plus row 3. Gives me a 0 here. Negative 4 times this, add it here, gives me 0. And now pay very close attention what happens. When I multiply this by negative 4, I get negative 20. I add it to this, I get a 0. Whenever I multiply this by negative 4, I get positive 12. I add it to this, I get 0. Now, we have a little bit more work to do, but you can see immediately this departs from the other problems that we have done where we have regular old solutions, regular old consistent solutions. Because at this point, in the process of trying to put a 0 into this location, we annihilated the possibility of having a 1 there. There's no way to get a 1 there. I know that you may think that if you manipulate it a little bit more, you can still get a 1 down there. But when you get all zeros across the bottom row of a matrix in the course of trying to get your diagonalization happening, you're done. You can't fix it. You can't make it and beat it into that form, because there is nothing that you can multiply a row up here by and add it that's going to put a 1 here while not screwing up what we've done here. I mean, you can put a 1 there if you want, but in the course of doing it, you're going to accidentally put 1s in these locations, which is going to screw that up. So once you get zeros there in the course of doing what you're trying to do, you're done. You can't do any more. All right. And so what I want to do now is, even though we're kind of done as far as that, I want to try to clean it up a little bit. We can put a 0 here. You don't have to do that. But let's move this matrix up above. This matrix, the one that we just wrote, I'm not going to change anything. It's going to be 1, 2, -6 with an 11 here. And then I have 0, 1, 5, -3, and then I have all zeros. That's what I just arrived at. I haven't changed anything. And I don't think there's any way that I can get a 0 here or a 0 here, because there's nothing I can multiply this row by and add it to this and add it to this that's going to make that zeros. But I can get this to be a 0. So let me go ahead and say that I'm going to take -2 times row 2 plus row 1. So if I multiply this by -2 and add it, I'm going to get a 1. Multiply this by -2 and add it, I'm going to get a 0. -2 and add it, then this is going to give me -10, and then I add it to this, I'll get -16. -2 multiplied by this will give me +6, add it to here, I'll get a 17, like that. And then the middle row, let me leave it the same, 0, 1, 5, -3, and then 0, 0, 0, 0. That is about as far as you can go. You see, you're attempting to get a diagonal matrix on the left-hand side. You're attempting to do that, but you hit a roadblock, because in the course of putting a 0 here, you accidentally get zeros in other locations, and you can't recover from that. I was able to put a 0 here, but there's no way to put zeros here, because I can't multiply this row or this row by anything. Well, I could multiply the second row by something and try to get rid of this and make it a 0, but in the course of doing that, I'm going to screw up the 0 that I just put in that location. So it's like it's just like something that gets away from you. You try to fix one thing and you screw up 2 more things. So this is sort of the stopping point. You try to get it as diagonal as possible. We've got 1s here, we've got zeros everywhere else that we possibly could, and I think we're done. There's nothing else that we can really do that's going to not screw up something else. So at this point, we write down our system of equations. The first thing we write down is we say that this is x, y, and z. This column is x, y, and z. So what we have is x minus 16z is equal to 17, right? This guy is telling us is that y plus 5z is equal to -3. That's a negative there. And the third thing it's telling us is that 0 times z is equal to 0, right? Now, we've come across this before. There's any value of z you want to pick, any value of z you want to pick at all that's going to satisfy that equation. Any of it's going to work. Pick 5, pick 10, pick -3. It's going to satisfy the third guy. So what you need to then write down then is say that z can be allowed to vary. It's allowed to be anything you want. And I'm going to circle that because that's going to be important. All right, and then we go up to x and y up here, and we realize that we can rewrite x and y. We can say that x is equal to 17 plus 16 times z. We just take this and move it over there. All right, and then over here we say that y is equal to -3 minus 5z. So we solve for x and y in terms of the variable that we're allowing to vary and go all over the place. And now we can get down to brass tacks and sort of write the final solution. So for, let me go ahead and switch colors here to black. So for x, this equation is 17 plus 16 times z, but we're allowing z to be k. So we'll just write it like this. Y is equal to -3 minus 5 times z, but we're allowing it to vary and be k. And z we're just saying is equal to k. So this is how you could circle it. I mean, this is perfectly valid. You're just saying that, hey, we're just allowing k to be anything, and when you pick a number for k, you're locking down the values of x, y, and z. that are associated with that according to these relations. So there's an infinity set of solutions, an infinite set of solutions. But if you were going to write it in terms of the linear algebra way of writing things down, in terms of solution spaces like this, the way you would write it down is you would say, that's the unknown I'm solving for. So I have a column vector, x, y, z, 17 goes in the x position, -3 goes in the y position. There's no number by itself for z, so I just put a 0 there. And I write it as a linear combination of this column vector with k, where I put a 16 there for x, -5 for y, and simply 1 for z. And the way you read that is you read it straight across. So this big X represents all of the variables that I'm basically solving for, but really it's x, y, and z. So x would be 17 plus k times 16, exactly what I got there. Y would be -3 plus -5 times k, exactly what I got there. Z would be 0 plus k times 1, exactly what I got there. This, in my book, is perfectly okay. This is typically how you're going to want to write it down on a linear algebra test. It's showing a couple of things. It's showing that you know how to manipulate a system, determine that it's a dependent system, that it's basically dependent on the value of some variable that you just choose and let vary for you. And it's allowing you to write the solution as a sum of two different column vectors like this, or two different column matrices if you want to use that word. So that's basically it. That's how we determine if a system is going to have an infinite set of solutions or not. The big clue is that as you do your row reduction, you get all zeros along one of your rows. That's the point at which you're going to start to have issues and have problems. So that is all I have for this lesson here. Make sure you understand it, make sure it sinks in, solve it yourself. Follow me on to the next lesson where we're going to continue working with systems of equations and getting a little more understanding each and every time that we work one of these problems.